Hi everyone. Yeah, good afternoon and good evening. And in today's talk, Henry and I, we are going to talk about the ARM MPAM extension support in Xen, which will cover several parts. But before that, I want to say something in advance. As we know, high-performance hardware platforms are currently entering automotive systems due to the trend towards centralized EE architectures and new compute-intensive applications. However, most of those in the market today have significant shortcomings in delivering predictable performance for time-critical applications. And the main reason is that these platforms are designed or optimized for average performance use cases. And at that time, they were designed delivering predictable performance for time-critical applications are not their priority, and this fall represents a major risk in the development of current and future automotive systems. And most of the technical engineers have tried to find some great methods to improve the predictable performance in software, such as cache carrying we have mentioned in the Xen Summit already. But they are not so convenient and have some limitations. And they can't cover other scenarios such as limiting DMA or limiting CPU memory bandwidths. And in this slides, we will introduce MPAM, which describes how and should reconcile between high performance and predictability in future hardware and software platforms. And this goal can only be achieved through close cooperations between system vendors and semiconductor companies, IP vendors, and OS hypervisor vendors. And we will introduce why in this presentation. And as one of the most important open source hypervisors, Xen is bound to participate in this area. So in next pages, Henry will introduce ARM's MPAM technology, as well as his proof of concept of the thing. And Henry, can you continue?
Thanks, Wei, for the introduction. I will start the talk from the introduction of MPAM, which will basically cover why we need MPAM, what is MPAM, and a brief introduction of MPAM principle. After that, I will introduce the MPAM configuration and how we implemented the MPAM proof of concept in Xen. A live demo will follow up as a showcase of our current work, and before today's talk ends, I will introduce the future work of the MPAM support, and we will have a short Q&A for questions. So firstly, let me briefly introduce what is MPAM. I would like to start from the question of why we need MPAM. We all know that in most of the current computer systems, multiple applications and VMs are running concurrently. On these systems, software may have impact on each other. So here is an example. In this figure, process A and B running on separate cores in the same cluster and therefore share the cache. The cache would be level 2 or level 3 depending on the hardware implementation. If process A is more data intensive than process B, then process A can cause all the cache lines that process B allocated to be evicted. Evicting those allocated cache lines can reduce the performance of process B. We need to take some actions to properly partition the cache in this case so that both processes can not be affected by each other. Also, in some other scenarios, some of them have already been mentioned by Wei in the beginning. For example, when combining two or more computer systems into one single system, it is necessary to isolate the performance of the real-time part from others in the integrated system. Or when foreground and background jobs are running on the same system, the foreground job's response time should not be compromised, and the background job's throughput should be optimized. Or when a server runs multiple VMs for different users, it is necessary to prevent one VM from using more resource than it has paid for, and therefore prevent other tenants from being able to use the resource they have paid for. No tenant should be able to overconsume resources. In all of these use cases, we need to bound the effects of misbehaving software on the performance of other software. Currently, like Wei said in the beginning, we can use existing solutions such as cache coloring to mitigate this problem. Cache coloring is a great solution, but is known to have some limitations. For example, the cache coloring technology depends on the hardware cache implementation about the cache weight and cache set. Also, the cache coloring technology places a requirement on the memory allocation of the OS or hypervisor. A special memory allocator is needed to support this. The ARM MPAM extension is designed to address problems that we just talked about in the system level. Also, the MPAM extension extended the controls of the shared memory system resources to not only the shared cache, but also the memory bandwidth, DMA, and the interconnect bandwidth. The full name of MPAM is Memory System Resource Partitioning and Monitoring, and it is an optional extension to ARM v8.4 and later versions. A full utilization of the MPAM extension requires the CPU support and the hardware support in the system. For example, the MPAM Aware Interconnect, SMMU, or memory controller. The main functionality of MPAM includes the memory system resource partitioning and memory system resource usage monitoring. There are basically 4 types of partitioning control interfaces in MPAM, namely portion, min-max, priority, and proportional stride partitioning. They are illustrated in these figures. Hardware can optionally implement any numbers of controls according to the need. Speaking of the memory system resource monitor, there are 2 types of resource monitors, namely the cache storage monitor and the memory bandwidth monitor. Similarly, hardware can optionally implement the types and instances based on the need. Now let me introduce the basic MPAM principle. In the right side figure, this describes the MPAM system model, where the behavior of requesters, interconnects, caches, and memory controllers are listed. In this model, there are 2 types of components, PE and MSC. A PE, for example, the CPU, refers to the component that generates or tags the transactions, and the MSC refers to the memory system component that contains the memory system resources to be managed. All paths that are marked as a red star in the figure indicates there might be an MSC in it. A memory system request begins at a requester, such as a PE, IO requester, and a DMA controller. MPAM information such as part ID, PMG, and MPAM space is transported with every request. An MSC responds to the MPAM information that arrives as part of a request. If the MSC implements the partitioning controls, those controls find partitioning settings by the part ID in the MPAM information of the request, and they use those settings to control the allocation of a controlled resource. For the virtualization environment, only physical part ID is available on the interconnects, but PE and SMU can translate virtual part ID to the physical part ID. In more detail, software assigns part ID that PE uses to label memory requests. Note that each PE has per execution level MPAM part ID and PMG, defined by software writing the MPAM NELX registers. The N in the register name is the exception level that supplies the part ID and PMG of the software execution environment, and X is the exception level that MPAM is controlled from. A memory system partition is associated with a software environment on a PE by loading an MPAM NELX register. Part ID is carried in interconnects and stored in buffers and caches. As I have mentioned in previous slides, the actual resource control is done in the MSC. The MSC is MMIO accessed and offers a number of controls based on the hardware implementation. For example, as shown in the right side figure, an MSC might have the cache portion or cache capacity partitioning for the cache and have the minimum and maximum limit partitioning for the memory bandwidth or SMMU. In this slide, let's go a little bit deeper and see how the MSC control is programmed. The MSC has a series of memory-mapped registers for software to program. These registers cover various aspects, including feature identification, part ID selection, and MPAM control configuration, etc. Note that there are separate MMIO registers in the secure and non-secure address spaces for accessing or controlling the related space accordingly. As shown in the right side figure, there are settings tables in the MSC that hold the settings for each part ID. Part ID selector connects all the interfaces to rows of all settings tables for that part ID. To set or read an MSC control settings, software should firstly set the part ID selector, then read or write settings via the interface registers. If a specific part ID comes with the memory transaction request, the MSC will pass the corresponding settings to the resource regulator, and the regulator will provide the resource on demand based on the feedback. The last part of the MPAM introduction is related to the context switch. We have covered this a little bit in the previous slide. Each PE has per execution level MPAM part ID and PMG, defined by software using the MPAM NELX registers. The right side figure gives an example. MPAM has the same context switching requirements as other PE states, so if we return to guest from Xen, the MPAM 0 EL1 and MPAM 1 EL1 need to be context switched for the correct guest software environment. I will cover this more in later sessions when talking about the implementation in Xen. So in the next section, I'm going to talk a little bit about how to configure MPAM if we want to use it. Normally, to use MPAM in Linux environment, we need to tell the Linux kernel or hypervisor about the hardware information through the standard interface. On ARM, both ACPI and device tree can do this job. But here we use the device tree as the example. The device tree here provides an example of the CPU and cache topology of a two-cluster ARM v8a platform. Each cluster has its own level 2 and level 3 cache. To make the example simple, here we only illustrate the MSCs to control the level 3 cache. So according to the MPAM device tree binding, the MSC node is placed as the subnode of the level 3 cache. One note here is that with this setup, we have two clusters in the system, and cluster 0's CPU should not be able to access the cluster 1's MSC memory mapped registers. So we need to handle the CPU affinity implied by the MSC parent cache node and set the limitation accordingly. With this device tree configuration, in the next few slides, I'm going to introduce our work about the MPAM POC in Xen. I will start with the MPAM at the boot time, where most of the initialization work is done in this stage. The first one is setting the default value of the MPAM system registers. According to the MPAM specification, some of the MPAM system registers reset to the architecturally unknown value. So we need to take care of this. We need to make sure that these registers are reset to 0, so all the guests are assigned to the default partition in the beginning. Then, like we are currently doing for other ARM architecture extensions, we check the ID registers in the top right side table to discover the MPAM CPU feature. The next step is the MPAM initialization, and we start from the detection of MSC from firmware. So here I use the device tree as the example, and the detection and initialization is based on the finding of the device tree node that contains the MSC compatible string. Note that, as mentioned in the device tree slide, we need to take care of the MSC CPU affinity if the MSC is related to cache. The MSC detection is followed by data structures initialization. On the bottom right figure, I draw a simple diagram about how we organize our data structures. To properly configure different types of MPAM resources, we abstract the resource concept in MPAM to two kinds of grouping, namely the MPAM class and MPAM component. An MPAM class is the set of components of the same type. An MPAM component is a group of MSC or RIS that control the same thing. For example, the set of MSC or RIS that make up the level 3 cache are a component. These are sometimes term slices, and they should be configured as if they were one MSC. So because of the SoC probably has more than one level 3 cache, each attached to a distinct set of CPUs, all the level 3 components are grouped as a class. The MPAM boot time initialization will end with the probing of MSC supported hardware controls and reset all of them. Then in the domain creation stage, Then we'll assign a part ID for each domain and context switch them at runtime. After the MPAM initialization, at runtime, if we want to apply the MPAM config to domains, we need to use Xentool. Xentool already contains a set of commands that originally designed for the x86 Platform Shared Resources, or PSR. This tool basically allows users to determine and monitor the usage of cache or memory bandwidth per domain. The full list of subcommands are listed here as a reference. In the right side table, I made a comparison of PSR with MPAM, and it is quite clear that the most of the functionality of these two are similar. So for MPAM implementation, we reused the xl-psr framework in Xentool. The xl-psr based on a set of hypercore OP and sub-OPs. So here I listed the sys controls and DOM controls used by xl-psr. The black ones are those that we have implemented. As you can see, they are basically related to the control of the level 3 cache, and the gray ones are unimplemented ones. This is basically due to the lack of hardware with related MPAM features. So I would like to note that since MPAM supports more than only the level 2 and level 3 cache, for example, MPAM also supports SMMU. So in the future, I think we will add more sub-ops specifically for ARM platform. Apart from the guests created from XL, we also need to handle some extra cases such as the DOM0 itself and the DOM0 DOM use. For DOM0, we define a command line interface that user can leverage to provide the MPAM configuration for resources. And for DOM0 DOM use, we define some device tree properties. Then we'll pass these command line options and device tree properties at boot time. Then we'll apply them to the domain at the domain creation stage. So now let's go to the live demo. The live demo is carried on the ARM fixed virtual platforms, aka the FVPs. These fixed virtual platforms are complete simulations of an ARM system, including a processor, memory, and peripherals. These are set out in a programmer's view, which can give us a comprehensive model on which to build and test our software. So for today's talk and demo, we used the FVP base with two ARM v8 clusters. The command line attached here shows the full parameters of running them on the FVP, with the MPAM related parameters highlighted. Using this setup, two clusters are set up with MPAM version 1.0 and related level 3 caches to be controlled by MPAM. The related device tree is the same as the one in the MPAM configuration section. So I have recorded a demo video with the FVP setup in the previous slide. Now we can play this video. Now we can see that we start the FVP, and from the log printed here, we can see we can use telnet to connect to the serial port of Xen and DOM0, which is port 5000. And if we connect by telnet, then it's booting now. So while we wait for the booting of DOM0, we can scroll back a little bit to see the logs printed from Xen. Like we have covered in the implementation session, the Xen command line here contains a MPAM part with a bit mask for the level 3 cache configuration. You can see here. And later, then we'll detect the MPAM extension during the CPU feature discovery process. And also in the boot time, then we'll discover the MSCs from the device tree. And eventually, then we'll enable MPAM with the number of part ID and PMG supported by the hardware. Then and DOM0 will boot as usual after. So now we can probably fast forward it a little bit to save our time. And go here. Now we can see the DOM0 has booted. We will use root to log in and see the XL help. We can see the xl-psr related command appears, and we can use the xl-psr hardware info to see the MPAM related hardware information. And it is shown here. For example, the level 3 cache size, a maximum part ID supported, the default cache portion bitmark length, and default bit mask is shown here. We can use the xl-psr cat show to see the current cache portion bit mask for domains. You can see that we only have DOM0 for now, and this value is inconsistent with the one we provided from the Xen command line. And also prepared a guest image and config in the rootfs of host to start a simple guest. You can see this is a pretty simple guest that contains only a kernel and a disk with 1 CPU and a half gigabyte of memory. We can start it use xl create, and then we'll pass the config of this one, and we also here can fast forward a little bit to probably here. So now you can see the guest is started, and while the guest is booting, after the guest is booted, we can use the xl-psr pet set command to set a portion bit mask for the guest that we just started. So here I use the help to check the style of this command, and we use this command line to set a bit mask for the DOM-U1 that we just created. After that, we can see the bit mask of the DOM-U1 by the xl-psr cat show. So now you can see that there are 2 domains, and each one of them has its own cache portion bit mask. So this is basically pretty much everything from my demo. Also, the last section from my side is the future works. So in the future, I think we need to enable more types of resources, such as the SMMU and the memory bandwidth. Once we have the hardware that implements these features, of course. Besides that, the monitors of different types of resources are needed. Also, we need to provide some numbers of the performance with and without MPAM, since normally on FAP, we cannot get a reliable number as the FAP is only the simulation. One more interesting part is the support of vpart ID, which in the virtualization environment means partitioning the memory system resource for the processes running in the guest based on the Linux kernel MPAM support. The final one is the ACPI support of MPAM. This would allow us to describe MPAM in a modern and more cloud-based environment. So here I attached the official MPAM ACPI table specification. And now I think me and my colleague Wei Chen are open to questions. So any questions about the MPAM, please let us know.
Hi Henry, hi Wei. A question regarding MPAM. So who allocates the MPAM part ID?
Henry, yeah, there is a question from the room. So who allocates the
Yeah.
part ID?
Wei, do you want to take this question, or I will
Yeah.
answer this?
Yeah, the hypervisor will allocate the part ID for which machine.
So hypervisor.
Hypervisor.
Yeah.
So is it
And
like? Okay,
sorry,
go ahead.
and there already have problems we have encountered that because the part ID and the VM ID is not the same size. Yeah.
So at the time of domain creation, the part ID is given. Is that correct?
Yeah. It should be. Yeah.
Okay, and it's unique for each domain, the part ID. The MPAM
And
part ID, will it be unique for a domain?
and the MPAM part ID will be unique in this VM's life cycle, but the part ID, but the part ID can be reclaimed, and also you can assign another part ID for each. It's okay.
Actually, one more question. Sorry.
Yeah.
You showed a device tree property. How does it relate to the part ID? I think it was on slide 7. You were showing some device tree property.
Yeah. Let
MSC
me.
something.
Yeah. I think the device tree is just the description of the hardware, and it does not necessarily need to have the connection with the part ID. So the hypervisor itself will be the one that manages the part ID in the system.
I think here the thing is, in theory, you could have several guests using the same partition ID.
Okay.
You could create a group of guests that would share an amount of resources.
Okay.
Because if you are on a safety example, what you want is isolate some resources for one or several safety domains. From and let the rest of your system use what is remaining. So it could be that you have one RTOS using 1/10 of the cache, and then one other RTOS using 1/10 of the cache, and then you will say that all the other guests they just need to use the remaining part. So that means they would all share the same part ID, possibly. But right now it's.
Yeah, but Bertrand, how does that thing about the part ID tie to this device tree description, the one where the CPU is getting tied to the cache? So
For now, it does not. In the POC status, it's one guest has one part ID.
Okay.
And at this stage, we have very few hardware support, so it means that it's a POC at this stage, which needs to be discussed. But that's the kind of discussions we need to have. How do you allocate the part ID? Is it something created by Xen? Is it something linked to, I don't know, CPU pools, for example, or something else?
Okay.
That's an open question at the moment.
Okay.
Right now, it's one part ID, one guest.
I see. And is it something similar to the static partitioning thing, the part ID, or both are different concepts?
It's part of the static partitioning. That's static partitioning of hardware resources. The problem is it depends on what you have supported in your hardware.
Okay.
And right now, the only example we have is about L2 cache. So it's another way to do what you could achieve with cache coloring, maybe.
Okay.
But maybe not. That's why it's
okay.
At this stage we have very few hardware examples. That's only models. We have no real hardware supporting that, but no accessible hardware supporting that.
Okay.
I think that's it for the question from the people in the room.
Okay. So I will stop sharing from that.
Yeah.
Thank you.
Thank you.